So I'm going to give a little overview, and then that I should be able to get through now. And then observations, that's from meteorites to exoplanets. Mainly our solar system, circumstellar, just extrasolar planets get a lot of attention, but we really don't. We don't know a lot about them, and therefore they don't influence our theories of planet formation that much. That may change during the careers of many of you, because there are so many more planets out there, but not the case yet. Disks, environments in which planets form, models of solar nebula, the region in which the sun and the planets form, and planetesimals, the solid bodies out of which the terrestrial planets and the cores of the giant planets are thought to have formed. Disks, the growth of solid bodies, delivery of volatiles. Volatiles means melt and vaporize at low temperatures to terrestrial planets. People talk about Earth as the water planet because 2/3 of Earth's surface is covered with oceans. But if you look at a cosmic mixture of things, now if you have a material that formed the sun and the planets, and you can cool it off and condense it in, as John Lewis's models that Ted showed in the first talk, you get some rock, and then you get a comparable amount of water ice if you get colder in terms of mass. But water is less than 1%, well under 1% of the mass of Earth. Just the thin layer. It's lighter, so that's why it's on top. But it's a tiny amount, less than 1/10% of Earth's mass. So it was too hot, actually, for water to condense. But we didn't get, that's why we didn't get very much water. We got a little bit thrown from outside in. Exactly where that outside is, asteroid belt, comets, that's somewhat controversial. And some mixture, we know that. The amounts. The volatiles, and not only the water, but the nitrogen, carbon, came farther out, but probably not from around this distance. It didn't solidify here. Came in later from the asteroid belt or from comets. And then the accumulation of the giant planet gaseous envelopes. This art was on the front piece of both of my lectures, and I'm going to explain it in a little more detail now. This is the sun. Young sun, proto-sun, growing sun. There was a disk of gas and dust, started with a giant cloud of molecules, and gravity force brought this cloud in from about a light year across. It's actually a core in a cloud. It shrank much, much smaller. Now, gravity just wanted to keep it shrinking. But as it shrank, to first approximation, it was conserving angular momentum. And just as a dancer or astronaut, if she moves her hands closer to spinning and moves her hand close to center of a rotation, she spins up faster. As material goes to the center, it spins up faster. angular momentum of a spinning body is proportional to the rotation rate and to the moment of inertia, the spread. And the moment of inertia goes as the square of the size. So if it shrinks down by a factor of 10, then it's going to spin up by a factor of 100. And if it shrinks down from a light year, the distance light travels in a year, to something much smaller than that, something of around 10 light seconds, we're talking about a factor of 1,000,000 shrinkage. And that means it spins up by a factor of something like 1,000,000,000,000. Well, even a very slow rotation will mean it's going to go really, really fast, and the centrifugal force will throw things out. So it would rip itself apart. So it actually can't all fall in. It falls in as close in as it can, but still conserving angular momentum. And that the portions near the rotation axis fell in right onto the star, growing a star, and the material from farther away fell in as far as it could, conserving angular momentum, and formed a disk in orbit around that star. And processes in the disk dissipated energy and pushed some material, most of the material, in towards the sun, but a little of the material, with most of the angular momentum, moved farther away. And within that disk, the planets formed. Now that disk, just like the sun, was composed of a mixture of elements, more than 98% hydrogen and helium. But in the sun, everything was really hot. And everything was a gas, actually a plasma, ionized gas. But out in the disk, especially farther away when it was chilly, you could have many of the elements, many of the compounds condensing into solids. And what could condense depended on the temperature. The temperature is hotter close to the sun, just as it is today, but it's actually not for exactly the same reason, because it wasn't the sun that was heating the disk. It was the energy that it got from falling downward. Falling downward into a gravitational potential well, and that releases energy. The material moving faster, that's the first way the energy goes. Then, as it hits the disk, material hits coming from above and below. Kinetic energy dissipates. Some of it stays in the orbital energy, but about half of it is dissipated into kinetic energy. Some of that energy is radiated off into deep space, but other just keeps it warm, and it tends to be much warmer the closer to the sun, but not because of the sun's heat, because you've fallen farther into the gravitational well, at least at the beginning. Later on, as the disk clears out, then the sunlight becomes exposed to sunlight. But you have things that got hot for a little while and then cooled off. You have things that stayed warm. We know that some things didn't completely vaporize because there are some grains that show chemical signatures that could have formed in some very special stars that are rich in carbon, but could never form by natural processes that we know of in the solar system, including in the solar nebula. So there are some ices in comets that wouldn't exist if you cooled something quickly from solar nebula, or even just let it out for a while in space, because they're clearly irradiation products on ices, and this irradiation had to occur over very long periods of time, millions or billions of years, and that could be possible in interstellar space, but not on the time scale of the solar nebula. So our solar system provides various clues. The most obvious ones, the ones that were apparent to Immanuel Kant and Pierre-Simon de Laplace in the 18th century in their formation theories of the solar system, were that the planetary orbits were nearly circular and coplanar. So they hypothesized that the planets presumably formed in a disk of material when they had no idea about clouds in interstellar space or things like that. Those are 20th century ideas, 20th century observations. And the fact that planetary orbits are ellipses to a good approximation, Keplerian ellipses, is a property of physics, the dimensionality of our universe, and the inverse square gravitational force law, Newtonian physics. Newton can derive these from physical models, so there are going to be these elliptical orbits regardless. They don't tell us anything about the formation. But the fact that they're circular, very low eccentricity, and they're nearly the same plane, that's not physics. Physics does not demand that. It's a clue, it's a signature of how the solar system formed. Now, the solar system is a big body with some little bodies around it. But so are all the giant planets. They all have satellites much smaller than they are. And despite the fact that we have all these extrasolar planets, we have these mini solar system-like things that we have much better observations of, especially the Jupiter and Saturn systems, because we've had orbiting spacecraft. Now, near planets, you have satellites that aren't fully formed moons. They're small, tiny baby moons, collections of moons, ring particles, because they couldn't form. Because the tidal force, the tidal shear, is just too strong to allow bodies to gravitationally assemble. You can have small bodies that exist near planets because their material strength is much stronger. Electromagnetic, if you look at just fundamental forces, electromagnetic force on atoms are 10 to the 37 times stronger than gravity. So you can get bigger things. I'll finish the slide and then call it a day. Compositions. The largest bodies, Jupiter and Saturn, are the most gas-rich. Uranus and Neptune are intermediate. Everything else, very little hydrogen and helium. Among the small bodies, they're rocky near the sun, icy farther out. These are condensates. This is what could condense near the sun at temperatures in the disk. This is what could condense farther out. And icy generally means ice-rock mixtures because both could condense there. The compositions of bodies are incredibly similar, except for volatiles. The ratio of, say, silicon to carbon, silicon to lead to iron, etc., is the same in a meteorite as it is in the sun, and they're more volatile things are not as common, but if you go down to comets, which are colder temperatures, The oxygen is also the same relative to these rocky elements, and the carbon. The nitrogen and helium and all the noble gases and hydrogen are much lower relative to the sun. But it's amazing that the similarity in composition. Meteorites, even though compositionally, primitive meteorites are all very similar to one another, and aside from volatiles to the sun, you could see the ones I showed early on, they're very, very heterogeneous bodies on small time scales. And then geology, the cratering record. If you look at an really old surface, like the lunar highlands, which are 4.4 billion years old, they have 100 times as many craters as the lunar maria, which are about 3.5 billion years. So it's only 20–30% older, but 100 times as many craters, and that can only mean there was a lot more junk around early in the whole system of the solar, or early in the history of the solar system, than there has been subsequently. So anyway, that's just a little bit of an overview. I'm going to get into planet formation in much more detail tomorrow, but I think it's time for a coffee break. Thanks for your attention.